3, third problem in the set. And this one starts getting to vectors with the unit vector notation. So it says that at time 0, at 0 seconds, a particle leaves the origin with a velocity of 17.3 meters per second in the positive x direction and moves in the xy plane with a constant acceleration of -2I plus 4j. Just as a heads up, the notation where I got these problems, a bold letter denotes a vector. So I with a bold font basically means that it's I hat. Same thing with the j. So that's the acceleration rate, a, as a vector. At the instant the x coordinate of the particle is 18 meters, what is the x coordinate of the particle? So the particle leaves the origin with a velocity of this in the positive x direction. We need to start writing out some stuff in terms of vectors. So the position vector should be some x value in the I direction plus some y value in the j direction. We'll go ahead and put a little, for initial position. There we go, little zeros on there. The initial velocity as a vector would be some vx initial plus some vy initial in the j direction. And the acceleration is just going to be a constant because in this case, there's no time variable in there. So the acceleration is a constant, 1.2 I plus 4j. And that's meters per second squared. Probably going to leave off a lot of units here just because it'll get a little cumbersome trying to write all that in there. So the initial position of the particle, and then ultimately we want to be able to say that there's some final position of the particle. We don't know what that is. Something I plus something j. And all of these are going to relate together in the x dimension and in the y dimension based upon our standard physics formulas. Because we have a constant acceleration, all of our kinematics equations and formulas and whatnot will work. So they're giving us some information in the y direction. Let's go and erase that question mark j. It's going to be 18j. We want to know what that x component is at that moment in time. So if we know where it is in the y direction, we know the acceleration rate in the y direction, we know the initial velocity in the y direction, which we'll get to writing that in there. We'll refill this stuff because it tells us it's only in the x direction in the beginning. And we know the position in the y direction in the beginning, then we should be able to figure out using a kinematics equation just for the y information to find the time. And then we can put that in and look at x information. So let's go ahead and substitute some stuff out. We know that the original velocity is 17.3 in the positive x, so that would be 17.3 I. And there's no j, so that means that's going to be a 0. I'll go ahead and leave it as a 0 rather than deleting it completely. And it's in the origin at that moment in time. Oh, geez, man, we're coming up lucky here because we're getting goose eggs all over the place. Bunch of zeros. 0 position in the beginning, 0 initial velocity, acceleration 4, and new position 18. So if we want to write a y equation here, we're going to be pretty lucky. I mean, we're going to say 18 equals 0 plus 0 plus 1/2 times 4 t squared. So 9 equals t squared, t equals 3. Sorry, I just kind of skipped some steps there. That's 1/2 times 4 is 2 divided by 2, you get 9. I guess I didn't save any time if I describe it again. So it takes 3 seconds for the object to change its y position from 0 to 18, undergoing a constant rate of acceleration of 4. So we're given a 2-dimensional problem, but each dimension is independent. What happens in the y-axis happens in the y-axis, all right? What happens in the x-axis stays in the x-axis. So now that we've got that figured out, we can, essentially like a projectile problem, we can move time back and forth between the dimensions. It would be nice to be able to jump back and forth between dimensions like time does. So we can go ahead and say that in the x dimension, we should have a similar equation. New position, it's going to write a y there, dang it. equals original position plus original velocity multiplied by time plus 1/2 at squared. Now, you might be thinking, wait a second, why are we doing all this stuff for x? Well, this is not a projectile. This is something moving the xy plane, which can be just like a tabletop. So we don't know the new x position. We know the original was 0. The original velocity was 17.3. The time we just calculated is 3 plus 1/2 negative 1.23 quantity squared. Let's see what we get. My multiples of 17.3 aren't that good, so I'm going to use my calculator. 17.3 multiplied by 3 plus 1/2 times negative 1.2 times 3 squared gives me 46.5 meters. And so that's the x component of the position after 3 seconds. Now, you might have been able to try to whittle this around using the vector notation, but because you don't know the time, you can't have a complete equation for the position as a vector. So this is the best way to work it out. Let's go on to the next one here. More vectors. It says a particle moves in the xy plane with a constant acceleration given by a, again, bold here means vector. Vector a is equal to negative 5j. So it's only in the y direction. Negative 5 in the y direction, negative 5. That's like half of negative 10. Negative 10 is pretty much the acceleration of gravity. Interesting. Anyways, we're not necessarily in vertical motion here. At time equals 0, its position and velocity are 13 meters and negative 2 plus 9j meters per second, respectively. What is the distance from the origin to the particle at time 2.7 seconds? So it's, we don't, position and velocity are, okay. So sorry, my brain's getting a little flustered. So following the same sort of model that we just did, we can have an initial position vector. And that's going to be something in the I direction plus something in the J direction in meters. Then we'll have an initial velocity vector, which will be something in the I direction plus something in the J direction, meters per second. I'll go ahead and put the units at the end. And then we'll have an acceleration rate, which is something I plus something J, picking up the pattern here, meters per second squared. And then we should be able to write some sort of a formula for the final position as a function of time for this object. And it's going to, again, be something in the I direction plus something in the J direction. However, it's a lot easier in order to think of the position as a two-dimensional version of our kinematics formulas we have up here. It would be r at time 0 plus the vector v0 multiplied by t plus 1/2 the acceleration vector multiplied by t squared. So this is position equals original position plus velocity, original velocity multiplied by time plus 1/2 acceleration times time squared. Sorry, multiplied by time squared. So this works whether it's a one-dimensional, two-dimensional, 12 dimensions, as long as we have the I, J's, K's, and whatever else to keep track of it. So let's go ahead and rewrite these three vectors in terms of what's given to us. We know that it's going to be 0I minus 5j for the acceleration. They told us that. At time 0, which means in the initial part of the problem, the velocity is 13I, just 13I, so there's no j. So 0j. And I'm sorry, I got that totally backwards. I know you're thinking that. The position and velocity r, I should have known from grammar that was wrong. The position and velocity respectively are these things. So 13I is the initial position and 0j. And the velocity, let me go and erase some of these underscores here because it's going to be a little tricky to see what's happening. And the velocity should be negative 2I plus 9j. So we have vectors for the position, velocity in the beginning, and then the constant acceleration rate. So we can rewrite this formula to include all those things. And we could rewrite it further after this, but let's just go ahead and put it in as such. So we'd have 13i plus negative 2i plus 9j multiplied by t plus 1/2, and I'm totally running out of space here. And I scroll over, let's see. We don't need any other stuff. What's the distance? So we want the position at 2.7 seconds. Plus 1/2, my 2's are looking terrible there, of negative 5j t squared. So I can go back a little bit here. I don't need to be that far over. Doink. So we want to find out where it is. Plug in 2.7 seconds. So we'd have 13i plus negative 2i plus 9j times 2.7 plus, I'm going to go ahead and just distribute that 1/2 in there, negative 2.5j times 2.7 squared. Squeeze it in. I'm getting really lucky with the squeezing it in there. Let's calculate what that is. And then combine like terms. The i's make them like terms. So we've got 2 times 2.7. That'd be negative 5.4i plus 9 times 2.7 would be 24.3 j. And then let's see, 2.5 times 2.7 squared, we'd have negative 18.225 j. Now we've got a 13i, a negative 5.4i, we got a 24.3j, and a negative 18.225j. Combine like terms and get what the position is. 13 minus 5.4, we get 7.6i. And 24.3 minus 18.225, 6.075. Now that is the position vector, which is almost what they want. They want to know not just where it is, they want to know the distance. So the last step, and I apologize if I kind of flubbed this and didn't say this out loud, the last step is to find the magnitude. What's the magnitude of that displacement? So you'd have 7.6 squared plus 6.075 squared and square root it. Square root. As I'm making this video, it's we're approaching back to school night time, so hopefully I'll look at a watch. I'll find out that I'm not supposed to be in a class right now. So I get 9.73 meters. Let's go ahead and solve this last problem real quick. I know I'm kind of going really long on the video here, but this last one's kind of fast. Plus, this is like ASMR, but not quiet and not relaxing. I don't know what ASMR stands for other than something about sound. So we want to calculate what 2a minus b is with these two vectors. So 2a minus b as vectors would be 2 times the vector negative 2i plus 6j minus the vector 6i plus negative 4j. Numbers multiplied into vectors distribute just like anything else. So this would be negative 4i plus 12j, and I can distribute the negative inside negative 6i plus 4j, and this is supposed to be what the vector c is equal to. And if I simplify that, I'd have negative 10i and then plus 16j. So that's the vector c, and the magnitude of c would be negative 10, the quantity squared, plus 16 squared. I'm guessing that's not a pretty number. Let's see here. I don't remember 16 squared off the top of my head. Do you? I knew you didn't. 18.9 roughly. So whatever unit that is, that's what it is. What is 16 squared? 256. That's a beautiful number. So there we go. I just worked through some problems. Thanks for watching.